All right, so now we move on to lesson 9.3, part 1 and part 2 in this video, which is dealing with quadratic inequalities of two variables. Now, first and foremost, we can address the quadratic inequalities in two variables into the following formats. We can have it where y is less than or y is greater than, and those are strict inequalities. We can then go on to less than or equal to or greater than or equal to, and the important thing is here is that a, b, and c are all real numbers, because of course we don't want to have any sort of imaginary numbers. We want to have them all part of the real plane. And then lastly, we need our a coefficient to be not equal to 0, because if it's equal to 0, it wipes out all of the terms that are at the beginning of the quadratic, meaning that this becomes a linear term instead. So it's really important that a is not equal to 0. Now, throughout this lesson video, what we're going to talk about is, first of all, the quadratic inequality in two variables represents some sort of overall region in the Cartesian plane in which objects can be, or in which points can be described that are solutions to the inequality, where the quadratic itself is the boundary line, and then depending on which direction the inequality is facing, whether it be a less than or greater than, including the equal scenarios, we say that that represents a region or a solution region. Now, to solve any quadratic inequality in two variables, we determine that solution region as just mentioned, and the solution region may lie above or below the parabola, just depending on what the inequality looks like, and then we want to determine, based on that, are those actually solutions? We can always verify those things. Now, let's take a look at example 1, where we're going to look at potentially graphing one by hand here. So we have the following inequality. Y is greater than x minus 4 squared minus 2. Now, you probably recognize this format because it's actually the vertex form. So in the previous unit, we would have written, or in our first unit, we would have written this as y is equal to a times x minus p all squared plus q. What we're doing with this is, rather than thinking about it in terms of this format and how it's written, and then just talking about purely transformations like we did in quadratic functions, now we're going to talk about it in terms of solution regions, or given situations in which inequality represents the overall region of given solutions. Now, for this piece here, when we graph it below here, we need to do something to graph this appropriately, and we're going to rely on quadratic functions, which was our first unit. First and foremost, let's create a t-table here. So off on the right-hand side, I'm going to create a t-table, and then what I'm going to do is, in the first one, I'm going to write this as, or in the first column, I'm going to write this as f of x equals x squared, where we have x and y ordered pairs that represent specific points on the original graph. From our quadratic functions unit, we would have learned that we have the following points. We can take -2 and 4. We can take -1 and 1. We can take our origin, which is 0 and 0. We can take our next point to the right, which was 1 and 1. And then we could take our next point from there, which was 2 and 4. Now, these are all just inputs and outputs that match. For every x that we input into this function of x squared, we get a y in return. If you wanted this as a table of values, plug it into your graphing calculator as y equals x squared, then do second table, and you'll be able to get this. For my Casios, just go into your menu and table. You'll be able to solve this. Now, we want to describe the inequality points, or the points that make up the boundary line. I'm going to write this as the following. We're going to say y is equal to the x minus 4 all squared, and then minus 2 on the outside. So this represents our boundary line. What are the transformations that happen? Well, if the original was x, then the new x, if it was a minus 4 in the brackets, it means it's actually a plus 4. X plus 4 gives us our new x value. In terms of the y values, we go down by 2 units because that's our q value. Y minus 2, close the bracket. Now, algebraically, if we plug each of the original points, which are these, in for the x's and y's on the right-hand side of the column, here's what the points become. For the first one, we were going to get 2 and 2. For -1 and 1, this will transform to 3 and -1. For the next point here, we're going to get 4 and -2, which is obvious because that's our p and our q values. If we take 1 and 1 and we transform it according to the mapping notation, this is going to give us 5 and -1. And then lastly, we're going to have where it's 2 plus 4, which is 6, and then y minus 2 or 4 minus 2 is 2, and there's our new points. So what we're going to do is we're going to plot all of these points that are on the right-hand side here. These are the ones that we want to put into the graph that is given to us on the left-hand side here. Okay, let's do that. So starting off with the first one, 2 and 2. I go to 2 and 2, I put a point. I then go to 3 and -1. 3 and -1 is right here. We then go to our vertex point, which is 4 and -2. Then we go to 5 and -1. Lastly, we go to 6 and 2. And hey, look at that. we get a overall parabolic shape where it matches on each side or it's symmetric about both sides. Now, before I draw the line, we want to be thinking, does this parabola have a solid or broken line? That's really important to reference. When we look at this, the inequality symbol determines if it's broken or solid. In this case, it's going to be broken because it's strictly greater than this value. So at this, what we're going to do is we're going to put a dotted line that passes through these points with arrows on the end. Because it's a strict inequality, it must be greater than. These points don't actually exist, they're on the line. And then lastly, they're going to propose the following question: should we shade above or below the parabola? In this case, we actually go back to the inequality just like we did for our line. And because it's all the y values that are strictly greater than this value, that means that it's going to be all of the line or all of the points that are inside here. So we're going to sketch down, and we almost want to be very careful that we're not shading the boundary line, because if you shade the boundary line, you're almost assuming that the boundary line is included, which we do not want to. So hopefully that does a good enough job here. The broken boundary line should also help in that case there. Okay, so this is what it looks like, because again, we have it where broken boundary line because it's a strict inequality. And then secondly, we know that the y values must be greater than, or they must be above the red line. If they're above the red line, that constitutes the solution region. Now, I'd recommend we just highlight that right below, because this point is made in the bubble as well. If we have a boundary line that is a solid line and it represents the region that is within the, or above including this solid line, or below and including this solid line, that is for inequalities that include the equal sign. Otherwise, if we see that it is a strict inequality, it has a dotted line representing that it must be strictly less than or strictly greater than that piece. Now, for part B, what they're going to ask us to do is just test a point that's within that green region. So what I'm going to do is just scroll back up. I'm going to go over to, let's say, like 3 and positive 1. That point is supposedly in the zone here, or in this given region. So I'm just going to record it as 3 and 1. When I go down here, we're going to take that original inequality, which was y is greater than x minus 4 all squared, and then minus 2. I'm going to plug in the x and y. My y value in this point up above was 1 for our test point. So we're going to go 1 is greater than the x value, which was 3 minus the p value, all squared, minus 2. This is going to give us 1 is greater than 3 minus 4 squared is 1, 1 minus 2. Therefore, this is going to give us 1 is greater than negative 1. Yes, this definitely is true. This works. So this is a solution. 3, 1 is a solution. Okay, now determine algebraically if the point 2, 1 is a part of the solution. Well, we're going to do the exact same thing here. So rather than us picking some point on the graph that's in that solution region, they've given us a value. Let's plug it in. For y, it's 1, which is greater than the x value, 2 minus the p value squared, minus 2. This is going to give us 1 is greater than 2 minus 4 is negative 2 squared. Negative 2 squared is 4. 4 minus 2. 1 is greater than 2. No. Therefore, we're going to say, therefore, 2 and 1 is not a solution. There we go. And we're going to say not a solution. You could even say that it does not satisfy the inequality. That would be another sentence we can use. But if you say 2, 1 is not a solution, fantastic. This does the job. All right, let's go to our next page here. Here's the following situation. We want to graph the inequality on the grid below. Now, to graph the inequality on the grid below, what we're going to look at is, first of all, we want to write an equation for this before we graph it. So if I wanted to write an equation that I could type into my graphing calculator, I'm just going to take this y is less than or equal to this quadratic of negative x squared plus 2x plus 8. And I'm just going to set it as y is equal to, whoops, there we go, y is equal to negative x squared plus 2x and then plus 8. We're just going to write it as an equals so that when we go to our calculator and we go into our graph menu, we just type in all the stuff on the right-hand side here. Okay, now this is the equation that represents the boundary curve, because on this line, strictly the line that represents the quadratic, this is the boundary. State the values of all intercepts. Well, I'm going to show you the algebraic approach, but you could also do this in your calculator using the second trace function or the shift gsolve function if you have the Casio. Let's do this using the algebraic approach for our x-intercepts. To determine the x-intercepts, we're going to set the y value to 0. And maybe we should just write this out first and foremost. The x-intercepts There we go. Okay, I'm going to set the y equal to 0. This is going to be negative x squared plus 2x plus 8. There we go. Now, to solve this, we need to use decomposition. So I'm just going to use the x off to the side. We must multiply to make negative 8 because it's the outside terms multiplied together. Negative 1 times 8. And we must add to make the middle. The middle is 2. The numbers that will do this for me are 4 and negative 2. Now, plugging this in, we get 0 is equal to, whoops, I don't want to shuffle that. We get negative x squared plus 4x minus 2x, and then plus 8. I'm going to factor by grouping. So I group the first two, group the second two. This is going to give us 0 is equal to negative x minus 4. I'm going to factor out a negative 2, leaving me with x minus 4 in my second bracket. Now, putting together the bracketed terms I have here, I get 0 is equal to, we take out one of the common term, and then we pair together our two outside terms, negative x minus 2. There we go. Now, I'm not really satisfied with this. What I want to do is I actually want to factor out the negative that's attached to our second binomial here, just because that's a really, that form is pretty uncommon. So when I factor out the negative, I'm going to put the negative out front of all of the terms, write it as x minus 4. And then if I take out the negative from this binomial here and place it out front, what this leaves me with is x plus 2 for my second binomial. Perfect. Therefore, if we wanted to write our x values, remember, it's always just the opposite of what we see in the brackets. From our quadratic equations unit, if x was negative 4 in the brackets, it now is positive 4. If x was positive 2 in the bracket, now it is negative. And we could easily get those by setting them equal to 0 and then solving. Or taking x minus 4 and setting it to 0, x plus 2 and setting it to 0. Great. Okay, here's our x-intercept. So this helps us graph one piece. The other thing we can do is right away, if we know that this is general form, well, in general form, the nice piece is our constant value, which is this 8, this is actually the y-intercept. So you can write that in your notes right away, that if we know that we have a c value or that this is the constant value in the general form, it represents the y-intercept. So therefore, y is equal to 8. Awesome. So this is actually a lot of information for us. Let's plot out as much as we can on our graph to the right here. So first and foremost, I'm going to go to where x is equal to negative 2, and I'm going to put a dot here. I'm going to go to where x equals positive 4, put a dot. I'm going to go to where the y-intercept is positive 8. Let me just accurately count up. 1, 2, 3, 4, 5, 6, 7, 8. So right about here. And so what we're going to do is just put our dot there. And then in your calculators, this is what I'm going to recommend, is for part C, before we can fully graph this, we actually need to know where the vertex is, because all we know so far is the x-intercepts. And realistically, I mean, there's ways which you could do this algebraically, very, very simple, which would be average the x-intercepts. We know it's going to be at 9 in terms of, or we know it's going to be at positive 2, sorry, for the x value, actually positive 1, because that's the average of the two x-intercepts. It's right in the middle of this x-intercept and this x-intercept. When you look at it, you always have to be right between to be at the vertex. We just need to figure out what is the value for the y. So let's plug this into our graphing calculators in order to figure out the vertex here. When we do this, we're going to type in y1 is equal to, and we're just going to type in that original function, x squared, negative x squared, plus 2x plus 8. Then what we're going to do is we're going to do our commands. If you have the TI calculator, you'll do your second trace. And then in this case, because the a value is negative, we're going to do maximum. If you have the Casio, just going to be a touch different. Instead of doing second trace, we're going to go shift gsolve. And then from here, shift trace gsolve, shift gsolve, sorry, not trace, shift gsolve, and then just simply max. Now, in your graphing calculators, what you're going to find is based on this, we can say that therefore, once we've done those commands, the P and the Q, which represents the vertex, is equal to, we're going to get 1 for X, 9 for the Y. Or 1 for P, 9 for Q. Now, let's plot this on our grid here. So if this ends up being our solution, and we now have our x-intercepts to pair with it, let's just make sure that's touch needed there. There we go. Let's make sure we go plot this on the graph up top. So I'm going to go up here and go to 1 and 9, which is here. By symmetry, we know 2 and 8 is a point. And now what I'm going to do is sketch the line. But again, we need to be very careful with this and say, is the boundary line going to be solid or dotted? The way we know is by the inequality. If it is equal to and it includes the boundary line like this, then we can say it's solid. Because when they say y is less than or equal to, as soon as that equals there, you can just put a solid line here. So that's what we're going to do. We're going to write a solid line that crosses through the points, arrows on the end, of course, because we want to be very accurate with this piece here and say that this goes left and right to infinity when unrestricted. Now, our very last thing is just to be like, hey, once we have our x and y intercepts, we have our maximum, which is our p and our q value, where do we sketch on this graph in terms of above or below? There's not really a question to reference to in terms of like part A, B, C does not say where to sketch. So what we're going to do is we're just going to sketch that now that we have all this information. If it is less than the boundary line or equal based on the original inequality, what this means is that our sketches need to go below the boundary line. Below the boundary line is all of this region here. And I'm going to sketch that in, make sure I shade in the middle to get all of those values. And this would go to infinity to the left and the right underneath the red line, including the red line, because the boundary line is included, the inequality included equals. So we want to be very careful with that. All right, now let's go to class example 3, where they're going to give us some graphs and then just say, hey, can you tell me what the equation would be based on not only the boundary being either solid or dotted, but based on the equation that's given, or maybe not given, and we need to figure out. Starting with the first one, this one's a bit of an easy one. We have a solid line. So this line here is solid, and I know it's not super obvious within the notes here. When this red line disappears, it's kind of hard to tell. I want you to think this as a solid line. Therefore, here's what our graph is going to become. They gave us a function. They gave us x minus 3x plus 2 as the overall function of this that represents the line or the border. And in this graph, what we need to realize is that where is the shading? It's all below that line that represents the boundary line. So if it's all below, this means that it's going to be y is less than or equal to, because it's a solid line. Starting with our first x-intercept, it was x minus 3. And then our second one was x plus 2. There is the overall inequality that represents this shaded region. Okay, let's go to part B. The only difference with part B from part A is you notice the shading is in a different piece. They both are graphs that face upwards, but instead of it being shading on the lower region, it's now shading above the graph. It's above this line. And again, we want to be thinking about this as a solid line. And if this is a solid line, I want you to write, therefore, y must be greater than or equal to the x squared plus 8x plus 12. They gave us the function that represents the boundary line. So again, we're just going to write it out. All we needed to determine was it a greater than or less than, and did it include the boundary line or not? In this case, it does. Last one for this piece here. We're going to scroll down and look at this part C. On part C, what we need to look at is the following. We need to realize that they didn't give us some sort of function that represented the boundary line, and there's a couple really key critical details we need in order to put this all together. First and foremost, if they don't give you the overall function that represents the boundary line, let's point out a couple details that will be necessary. First and foremost, we have a broken boundary line. So this is broken. Okay. Now, if that's broken, the other piece we want to figure out here is we need to build the overall equation. We don't have the equation thus far, and it's a quadratic. We always, from our previous unit, needed to solve for the a value. It was really critical. When they gave us a graph, we were always missing the a value. I want you to put together a couple things here. The p and the q, this is at 1 for x, negative 4 for y. The x-intercept, which is here and here, the first x-intercept is at 3 and 0. The second intercept is at negative 1 and 0. Now, this gives us some options here. These are both x and y's. So in terms of the x-intercepts, these are what we call our x and y points. Those give us options to plug in. This one down here is our mandatory point, our p and our q. We need this in order to figure out the a value. Now, to follow up on this, let's go off onto our right-hand side. In our quadratic functions unit, we always started by writing y is equal to a, x minus p, all squared plus q. This is the vertex form. Okay, now we're going to plug in one of these points, and I'm just going to choose the 3 and 0, for example. 0 for y is equal to a, 3 for x, minus the p-value. Well, it's negative 1 in the bracket because it was positive 1 on the graph. That was our equation of our axis of symmetry at positive 1, so therefore it appears as a negative. and the q value is -4. Now this is going to give us 0 is equal to a, 3 minus 1 is 2 squared minus 4. This gives us 0 is equal to a times 4 minus 4. We add both 4's across, or we add the -4 to both sides. This is going to end up giving us that 4 is equal to a4. And if I divide both sides by 4, like so, I end up getting that my a value is equal to 1. Now, some of you might be like, wait a minute, if the a value is equal to 1, why did we just waste our time in solving that? Realistically, we always need to make sure that the a value is something specific, and we need to account for it being a changing value because it's not always the same for the graphs. Now, without doing this algebraically, this has been pointed out in this specific example. What if we considered that this is our vertex point? What are the next 2 points left and right? They are one left and one up, one right and one up, meaning that the points that are adjacent to this point, or that are next to, that come next to this position in terms of like exact values, are going to be 1 and 1 away, or 1 x position away, 1 y position away. And then the next point after that is 1, 2, and then 1, 2, 3, 4 up. And same thing on the right hand side, 2 to the right, 4 up. This is actually the original x squared graph, only shifted by translations up or down. And in this case, it's been moved to the right and then down. So there's only been translations. There's been no reflection. There's been no vertical stretch. And that's reflected by the fact that the a is 1. It didn't change the graph's orientation, and the graph didn't get wider or more narrow. It stayed the same. So if you were astute and you realized that, and you're like, hey, wait a minute, this is the original graph in terms of its points that are close, then you can just say, hey, a equals 1. But in this case, I would always recommend just solving for it. Okay, now of course, getting the a value wasn't the point of this. The point of this was to put together the inequality. So if we know that it is a broken boundary, we now have an a value. We know what the overall equation would become because it's from the vertex form. We're going to write it as this: y blank. I'm going to fill in the inequality in a second. We're going to write this as a minus, or x minus 1 squared minus 4. So it's in the vertex form. Our coefficient a equals 1, which we don't really need to write. Now we want to look at this and be like, is the shading above or below this boundary line? And what does it mean when it's broken? What type of inequality? Well, in this case, it's below the boundary line. It's all below that given line. So we're going to write this as starting off with less than. There we go. And then we want to look at this and say, well, if we know that it is less than, is it going to be equal? Not in the case of a broken boundary. Broken boundaries are strictly less than or strictly greater. So therefore, this becomes the solution. Now, for some of you, you might have put it together in the alternative form, which is using the x-intercept. So I'll write that below. Or we're going to write y is then less than, my first x-intercept was x minus 1. And which for this, if it's actually minus 1, it's plus 1 in the factored form. If it was plus 3, it's actually minus 3 in the factored form. So some of you actually might have written it in this form here. Okay, now let's carry forward into part 2, which is the applications of quadratic inequalities in two variables. Very, very similar, just going to follow a slightly different format, and then we're going to go into some strict applications of this. Okay, first and foremost, to solve word problems, we must summarize the translations from English into the mathematical expressions because that's really important. So anytime we see less than, we want to be thinking it must just be less than and not including. Greater than, just opposite, we're going to put our greater than symbol. Less than or equal to, we're going to put the less than symbol but with the equal symbol. Greater than or equal to, we're going to put greater than or equal to with the line below it. Not more than. Not more than means, first of all, it has to be less than the value, but it could also be equal to the value. As long as it doesn't exceed the value, we're good. Not less than, that means first and foremost greater, but then it can be that value, it just must be greater. If it exceeds means it must just be greater because we don't want to have it equal. If it exceeds the value, we don't want to have it stuck at that point. At least means it's greater than or equal to. At most means less than or equal to. And then lastly, not equal to. We put an equal sign with a line through it, representing that the two sides are not equal, the left and the right. Okay, now let's go into example 1 where it gets us to kind of play around with these based on some expressions here. Write the algebraic expression for each of the following. All numbers are less than 50. Well, if we pick a number, let's let it be x, then it must be that they're all less than 50. Perfect. And they said strictly less than. They didn't say it could be equal. The sum of two numbers cannot exceed 12. Well, if I add an x plus y, so I'm going to take two just random arbitrary numbers, x and y, I add them together. If it cannot exceed 12, it just means it strictly has to be where it's less than or equal to 12, because if it's less than or equal to 12, even if it gets to 12, as long as it doesn't go to like something like 12.1 or let's say 13, we're good. A number decreased by 7 is at most 4. Well, another way to write that is x minus 7, which let's take a number and decrease it by 7. This is at most, meaning less than or equal to the upper bound, which is 4. A number decreased by 5 is not more than another number increased by 2. Well, when they say not more, when we look at this, we say x minus 5. We're going to take a number and decrease it. It's not more, but it definitely could be equal to, based on that sentence. If as long as it's not more, that means it could be equal. It just can't be greater. So we're going to write this as x minus 5 with y plus 2 on the other side, because it's one number decreased by 5 is not more than y plus 2, which is another number increased by 2. Lastly, if we take the sum of two numbers, it's more than 5, but less than 25. The way to write this is it's a lower bound, upper bound problem. 5, which is the lower bound, is less than the x plus y, which is the sum of the arbitrary numbers, but these two numbers cannot be greater than 25. They must be less than 25. And when we put these strict inequalities here of x plus y is greater than 5 but less than 25, it's because they said it must be more and less, not at most and at least. If they use that terminology, then we could throw in the equals. Okay, let's push forward here. Here's our first application example. It's going to involve a satellite, and this satellite is receiving signal for, let's say, TV, radio, whatever it might be. And so in this satellite, what we have is that we have dimensions where it is 60 centimeters in diameter, or from edge to edge, and it's 20 centimeters deep from the peak to its lowest point. Now, at this cross section, we see that it is centered at 0, 0, which is the origin. And what they want us to do is sketch this and then determine an inequality for the satellite in which it receives the transmission. So what we're going to do is, first and foremost, I recommend just drawing some sort of basic cross section at the top of the page here. I want you to draw a parabolic shape that kind of crosses through the origin and then bounces back up. Mine tends to float a little bit above when I'm drawing this, so I'm just going to make sure I like shade this, indicating it actually does come down. And I'm going to write this as 0, 0, because they said it centers at the origin and then goes away. Now, if we know that this satellite dish is 60 centimeters in diameter, that means from end to end of this satellite is the 60 centimeters. So what we're going to do is we're going to put, first of all, over here, this is positive 30, because we go to the right by 30. We could also go to the left by 30, meaning this is negative 30. And as long as we have that covered, then we know that this represents a total distance of 60 from left to right. What we also know is that it is 20 centimeters deep. So from my highest point down to the origin, which is where it's centered at, we're going to write this as 20. All right, now let's fill in some points here. We put in our origin point, which was at the very bottom, or the minimum. We also have where it is 30 centimeters to the right and 20 centimeters up. We have on the left-hand side negative 30 centimeters, or 30 centimeters left and 20 centimeters up. And I'm just going to move that a little bit over just so it all fits. There we go. So now we have 3 points. We have a left point, a middle point, which is our vertex, and then a right point. Now, what we're going to do is we first of all want to figure out the following. In this situation, they said we want to determine where the signal can reach. The signal can reach anywhere, including the inside parabola here. So what we're going to do is we're going to shade all of this and say this represents the solution we're looking for. This is all the pieces of which the satellite could receive signal is all within this area here. Now, what we're going to do is to build out this equation, we know if it's a parabola, we're missing the a value right away. Without even questioning, you could say, hey, we know we have to solve for the a value. So step number 1, we're going to write y is equal to the a value, x minus p all squared, and then plus q. Now, we know we have to use our p and our q, which is representative of the origin. So if you wanted to, you could even write p and q below the 0, 0. What we need to do is pick some other point. So let's choose this one as our x and y. I'm going to write x and y here, p and q below the 0, 0. My y value is going to be 20, which is equal to the a, x, which is 0, sorry, not 0, but it is equal to 30, because we're looking at that x value on the right. and then minus p, which is 0, all squared. Q, it's centered at the origin, so we don't go up or down from here. Now, this is going to give us 20 is equal to a 30 squared. 30 squared is equal to 900, so we're going to write a times 900. We will then divide both sides by the 900 as such. And when we divide both sides by 900, when we reduce this as a fraction, it's going to give us 1 over 45 as a positive value. Now, hopefully this makes sense for us, because if we know that this parabola faces upwards, then it must be a positive a value. And a satellite dish is actually quite flat. So when we get a 1 over 45 for the a value, that should make sense because it's very like sprawled out. It's very flattened out towards the x-axis. Our diagram might not do the best job of this, but hopefully if you look at the diagram off on the left here, you're looking at this and being like, the disk is pretty flat overall. All right, therefore, here's what our equation becomes, or here's what the inequality becomes. Step number 2, we're going to go y. Well, if it's above and including the boundary line is solid in our example because it's a satellite dish. It's a solid region which the signal can bounce off of and hit. What we're going to say is that it is above that line and including that line, so it's greater than or equal to the a value, which was 1 over 45. And then because the p and the q were 0, it just leaves us with x squared as our overall function for this, or the overall quadratic equation for this. Okay, so there is the inequality that represents the region in which the disk can receive signal, or the dish, I should say, but disk would also be somewhat okay. All right, let's go down to example 3 here. Now, this one goes into almost previous unit material, which is the quadratic equation section, and it deals with this idea in which we can solve economic problems by setting up some sort of relationship between price and the number of people that go. Now, to help us out with this, what we can do is you can actually plug this into your graphing calculator to help you out. Let's just read it for the context. So in order to get the most out of the revenue from registrations for a camping trip, an adventure company needs to have as many campers as possible at a certain price point that is reasonable. If 15 people sign up, the price per person is $50. So that's kind of a base benchmark. The registration fee is reduced by $2 for each additional camper beyond 15. The relationship between the number of registrations and the revenue is given by the inequality as such, where X represents the number of registrations over 15 and Y is the total revenue. All right, write a quadratic inequality or graph it. When we want to graph this, I mean, we could do this somewhat algebraically to get a piece of it, but we're going to actually have to type this into our graphing calculator and get a table of values. So first and foremost, type this into your graphing calculator. Y1 in your graphing section, we're going to type in 50 minus 2x, which is the first piece. And then in the second bracket, 15 campers plus however many additional attend. Now, when you go second table or shift and then, or not, yeah, for the TI users, you're going to go second table. For my Casio users, you're going to click menu and table. What this is going to do is it's going to give you a table of values that you can then plot out on the graph on the right. To do somewhat algebraically, what I'm going to do is I'm going to take these from our quadratic equations unit, and I'm just going to take these two brackets or these two binomials and separate them and solve for the x's to get the x-intercept. So starting off with this, we're going to go x-intercepts. There we go. If I do the algebra off to the side, it's going to be 0 is less than or equal to 50 minus 2x. When I isolate this, it's 2x is less than or equal to 50. Divide both sides by 2, it's x is less than or equal to 25. So 25 is my first x-intercept. If I do the same thing for my second bracket, 0 is less than or equal to 15 plus x. I subtract 15 from both sides. It gives me x is greater than or equal to negative 15. I'm going to look at this and be like, wait a minute, this is extraneous. Because if I have a situation where this is something that is negative, well, we're not going to have a negative amount of campers in this situation, or we don't necessarily want to have it where it's in the negatives, because then it would mean potentially we're losing people when we want to actually be gaining people. So let's be very specific about that. Now, for the y-intercept, I'm just going to set the x value to 0. When I set the y value, or let's first of all write this out. So y-intercept, there we go. If I want the y-intercept, I set the value of x to 0. So this is going to become y is then less than or equal to 50 minus 2 times 0. In the second bracket, it's going to become 15 plus 0. Apologies for covering up some of that graph on the right-hand side. This will be y is less than or equal to 50 times 15. This ends up giving us 750. So now we have an x-intercept that we can plot and a y-intercept. 750, which is here. We have our 25, which is here. Now, we want a parabola that will connect these 2 points. This is why we need our table of values from our graphing calculator, because we're going to find that the vertex is going to be at 5 and 800. So I'm going to put a point there, 5 and 800. By symmetry, I can go to where it's 10 and 750, because we know these parabolas will maximize at that highest point and then be symmetric at every other point. Another point is where it is at 15 and 600. So I'm going to go to 15 and 600, which is up here, about there, perfect. And then another point we could put is something like 350 and 20. That was another one that I got in my graphing calculator. So I'm going to go to 20 and 350, and there's our other point. Now, do we connect this with a solid or dotted line? In this case, because the inequality was a included, or when we scan back up to it, it was less than or equal to, we must see this as, hey, you know what? It's going to be a solid line. Let me make sure I connect these with that solid line. So doing that, it's going to look something like this, and it will cap out at the very bottom there. Now, you could be thinking, do we need to include arrows on the end left and right? No, because the campers are going to be limited to from 0 to 25, and the revenue isn't going to go into the negatives unless they potentially put in some money and then lost that money. But for this situation, we want to consider it as positive revenue for a positive amount of campers that go. Okay, here's our overall graph. Now, what is the maximum total number of registrations that will generate a revenue of at least? At least is such a key word. That means that it must be greater than this 500 or equal to that 500. To do this, what we're going to do is we're going to actually graph this in our graphing calculator in y1. So we're going to type in that original function again, 50 minus 2x, which hopefully for you is already typed in, 15 plus x in the second binomial. In y2, what you're going to do is type in the 500. And what this is going to do graphically for you is it's going to create a horizontal line at 500 that goes across and then intersects at a very specific point, giving you the lowest amount of people that could attend, or the amount of people that it would attend to give you at least that $500 in terms of the overall revenue. So let's actually write out our instructions here just so we have them here. For my TI users, what you're going to do is you're going to go second, trace, and then intercept. For my Casio users, you're going to type in shift, gsolve, and then you're going to scroll over to where you see ICST. Perfect. And then I'm pretty sure this is actually ISCT. Perfect. Actually, no, just making sure this will be our ICST. There we go. And if I have that order wrong, then it's okay. But we will actually, it is the ISCT. There we go. I just want to make sure I'm getting that right, just so that when you go to your calculator, you're not getting this mixed up and being like, where's that key again? Perfect. Okay. So there's for my Casio users. Now, when you do this, here's what the value you're going to get for this piece. And we're actually going to go over to the right-hand side. Therefore, the solution for this, and let's just show it on the graph and then we'll summarize it. You end up getting that this is an intersection at 17,247 and 500, which means that if we're trying to make sure that we have the appropriate number of campers, or that this is the maximum amount of people that will allow this $500, because when we reread this, what is the maximum total number of registrations that will generate that revenue of at least 500? The maximum number is 17.247, but of course, if we round it down, here's the issue. If you round this down, you're actually going to be below the revenue. So when it's 17.247, there's no such thing as 247 of a person. So what we're going to do is just round this up and say, therefore, 18 registrations are required. Perfect. Because if we, like I was saying, if we round this down, what it's going to do is we're actually going to be below the required revenue, and we want it to be above. Therefore, our solution region for this is here. Perfect. So this will be all the situations which we at least get $500. Anywhere in that green region, anywhere in the overall yellow region, which is everything including the green region, this is all technically the solution region for the problem because this was where it was y is less than or equal to this given function here. All right, now let's go on to example 4. Example 4 gets us to consider the following. An arch that supports a bridge over a river is parabolic and spans a horizontal distance of 250. An equation to represent this overall parabola that represents the support is y equals negative 0.0048x squared plus 1.2x, where y is the height and then x is the horizontal distance and from one end. All right, write the inequality that represents the cross-sectional region between the arch and the river. Okay, here's what we got to do. First and foremost, let's draw out a parabola. I'm going to sketch out just this overall arch that represents the parabola. I'm going to sketch the water at the bottom of this because this was the support that was above the water. And then for the inequality, well, they told us that if this is representative of the bridge, so maybe we'll throw that note in here. Here's our bridge. Here's our water, which obviously is the ripple here. And we're going to assume that it's flat. So don't think because I did a squiggle line here, that means that it's going to be something that we have to like think about in terms of it's increasing, decreasing in terms of vertical. It's just a horizontal line. It's just to represent the water. The solution region that represents the cross-sectional distance between these two, between the arch and the river, is that inside piece. I want you to highlight everything that is below the parabola all the way to the water. There we go. So this is our solution region. Now, the inequality that will represent this is the following. We're going to write it as y is less than or equal to that boundary line of negative 0.0048x squared and then plus 1.2x. There we go. Now, what is the restriction on the variable? Well, first and foremost, we need it to be such that y is greater than 0. If y is not greater than or equal to 0, such that it is a real number, this means you're going to be below the water level. So we don't want to be in the water taking a swim. We want to be above the water line. And so our y value must be greater than 0. Now, graph this inequality in your calculator. For part B, when we graph it in our graphing calculator, what you're going to do is type in to your y1 negative 0.0048x squared plus 1.2x. There we go. And now I'm going to give you some window settings just to help you out here. In your window settings, these are what you're going to want to type in here. And I'll do them just below the box where we're going to type in the, or where we're going to represent our graph. So first and foremost, this is going to be 0 for x, 300 for x maximum, and 1 for scale. For the y values, or for the y's, mins, maxes, and scale, it's going to be negative 1, 100, and then 1 for the scale. Now, if you type this in and you type in the y1, which was given, which was our inequality, what you're going to find is that it's centered at the, it has its left-hand side at the origin. So we're going to write this as here's our one axis, here's our other axis. This is our y-axis here. This is our x-axis here. When we sketch this, the parabola is going to kind of have this overall look like this. Maybe just a touch different than this, but the window settings should pretty much give it this. And then again, our solution region for this is going to be the following. We're going to have it where it is shaded below. There we go. Now, if you wanted to, in the Casio and the TI calculator, in order to get this shaded underneath this parabola, as you see like I just did in the green here, what we can do is over off on the left-hand side of the y1, which is equal to, what you can do is you can make this the lower triangle for my TI users. If this is the lower triangle for my TI users, it's going to shade below. For the Casio users, you're going to want to go into your menu and you're going to want to go into the extra section, which is actually, I believe, F2 as the key. Once you click F2, it's going to allow you to adapt this, and then you can choose the function to be a less than or equal to, a less than strictly, a greater than or equal to. In this situation, we want it as less than or equal to. So that's going to be important. For my TI users, again, when you put this lower triangle, it means the less than or equal to, and it will sketch out the shaded region like the green one here. Okay, so here it is in your graphing calculator. And again, for all these problems that are applications, you're going to realize that they're all centered around being in quadrant 1, because in reality, we're not going to have negative values come up that much in reality. We want positive distances in terms of like a bridge length. We also want positive heights in terms of a y value. Now, it's not always the case, but it is the case for this situation here. Okay, now what we need to do is if we want to solve this second piece here, which is our part C, they say that the tallest mast of a ship is 37 meters above the water level. Can the ship pass under where the arch is 50 meters from one of the ends? To sketch this out on our graph here that we've actually put here, before we start typing in any values, what this looks like is they're saying, will it fit at this point here where it is 50 meters away from the edge? And realistically, we could even talk about it as 50 meters from the opposite edge here as well. So if we wanted to sketch it over here and be like, this is also 50 meters, whether the ship is on the left or the right going under this arch, we need to see if it will fit under at these points. Now, to do that, here's what we're going to do. We're going to do this graphically, and I would recommend doing this graphically. Actually, we can even do this algebraically. Algebraic might be the better way, but if we wanted to do this graphically, here's what you're going to do. So graphically, you can type in y1 is equal to negative 0.0048x squared plus 1.2x in your first. And then for y2, what you can type in is you can type in and actually, no, we don't want to do another y2 because we're searching for a specific x. What we can do is we can write in our TI calculators, we're going to use the second trace and then the value key. And when we do second trace value, what this is going to allow us to do is that we can then, in our next step here, we can type in x is equal to 50. And when we do x equals 50, it will give us a specific value for what is the y value at where x is equal to 50. And we'll write that out in just a moment here. So for this case, we're going to see that this is where x is equal to 50. For when we go into our algebraic approach, we'll list out what this value gives you. For Casio's, we're going to go into our shift, gsolve. We're going to then do the arrow key, or the F6, I believe it is, F5 or F6, depending on the version you have. And then we're going to type in yval. Now, when we do yval, this is what is going to allow us. It's going to ask you for a specific x. We're going to put in x being equal to 50 in order to solve for that y value. Okay, so this will give you whatever the y value is at that point being 50 from the edge, whether it be left or to the right, but in this situation, specifically to the left. But because we know it's symmetric, it can be the same. What we're going to do is then do the algebraic approach, and we're going to actually figure out what this value should be when we do it in our graphing calculator. So algebraically, there we go. We're going to underline this. To do this algebraically, the y value is 37. That's the desired height in which, or that's the mass height. That's the tallest mass going underneath. This must be less than whatever the bridge height is. Whatever the bridge height is the 0.048, typing in 50x squared for our x value, because that's how far we are from the edge, and then plus the 1.2 times 50. When we do this, we're going to get that 37 is less than, for the first value, it's negative 12. 1.2 times 50 is plus 60. Therefore, 37 is less than 60 minus 12, which is 48. Yes, this is true. So therefore, the mast will fit below. That is the way we want to wrap this up and say the mast of 37 meters will fit below. Perfect. And we highlight that. Perfect. You always want to include like a sentence or just something right below where you do this algebraic approach, because for the just for a general observer, they would look at this and be like, okay, 37 less than 48. Like they know that's true, but like what does that mean in terms of the context? So just be very careful. Now, again, this is the algebraic approach where they say that 37 meter mass will fit 50 meters away. If we wanted to plot this now, we now know when it's 50 meters away or it's 50 meters from the edge, it's 48 meters high. So what we are going to do is say, therefore, right below this section, the graphic section, the y value is equal to 48 when the x value is equal to 50, or that it's 50 meters away from the edge. And on our graph, we can then go up and just put that over here. So at this side, it is going to be 48. At this side here, it is also 48. You can basically connect the two sides here. There we go. So these are both 50 meters from the edge. And maybe I'll just use some arrows here to represent that that's the 50 meters from the edge, representing where it's 48 in terms of the arch is 48 meters high in the air. Okay, now, perfect, that's it. Now, you want to move on to your assignment at this point. So make sure you take a look at these textbook questions, complete as many as you can, and then if you have questions, let me know. All right, good luck.